මම කොයි හරි යන්ද ඔකට ඩිස්කනෙක්ට් උනේ. මෙතන මම මේ delay spread එක මං හිතන්නේ ඇහෙන්නේ නැති ඔය කට්ටියට. Okay, I hope you uh, heard the delay spread calculation, so it is not much difficult. Okay, so this is the delay spread. This is uh, the reflected path time, and L divided by the velocity, that is the direct path time. So if you get the difference between the reflected path and direct path, time difference between reflected and direct path, so it is the delay spread. Okay, and also so you know that the delay is related with the directly related with the phase of the signal. Okay, and the phase also you can find using the delay. Okay, and this phase can be approximated using the Taylor series, actually Taylor series expansion. Okay, this one can be approximated to this one. Okay, this value. Okay, so if you are given the the transmit receive antenna height and the separation and the frequency, you can find the phase difference. So using the phase difference, you can find this delay spread. Okay. Okay, and one point I asked, okay, so if this is a two-ray system, two-ray model, okay, can the received signal be zero? Can this received signal be zero? Just tell me. Just tell me. Can or can't? That is your.
Can't happen, sir.
Hmm?
Can't happen, sir.
Okay. Okay. So here you have one signal and here you have another signal, no? So what happened if this like, okay? So first signal you will be having like this. This is the first received signal, okay? So after delay, okay? So delay is again related with the phase, okay? So let's say that it have 5 phase shift. So your next signal will be like this. What happen if these two signal add? This is 0 phase and this is 5 phase, then this signal and this signal will cancel out, no? This is destructively added. This is destructively added. Destructively added. Okay. So, okay. So actually that is what we at once, that is what we can feel, no? The received power cannot be 0. Okay. But it can actually, because there are two parts, and if the two part signals are added destructively, so this signal will be maybe 0 or maybe reduced. Okay, actually that is the fade-in. Okay, multipath fade-in. That is the multipath fade-in. Okay, that is how the multipath fade-in happens. If the signals are destructively added, there will be a power loss. Okay, and if it is constructively added, what happens? The signal quality will be high actually, but the the higher probability is there to add the signal with destructively. Okay. Okay. So so this signal sometime can be 0 if these two signals are with 5 phase shift. Okay, with 5 phase. Okay. Okay. And you can see that. Okay, you can see that. So actually just read this. Okay, from here to here, just read. Okay, so you can see that. Okay, so 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 here, if this delta 5, if the phase difference is 5, okay, what happened? 5 equal this one, okay? For 5, HT, HR, and lambda D, okay? So you can find the D here, this distance, okay? So there is a distance D that this can happen, okay? For the given antenna height and receiver, the given receiving and transmitting antenna height, okay, for a given receiving and transmitting antenna height and given frequency, there can be a distance. This delta 5 can be 5. Okay, phase difference is 5. Okay, so you can find this D. Okay, so this D, at this D, what happened? If your transmitting and receiving antenna are with this difference, what happened? The received signal will be 0. The received signal will be 0. So your signal will be very weak signal you will be received. Okay? So this distance is referred as critical distance, DC. Okay, critical distance. Okay, so this one. Okay, so at DC, so you will have a zero power receiving. Okay, zero power receiving point. Okay. So just actually these things maybe we haven't discussed in our classroom, okay, but just see it, okay. So I hope you got it, okay. Okay, so your first question will be maybe mainly related with this these things, okay. I hope you will be able to get 25 marks for that questions, okay. For each question you will be having 25 marks, okay. There are 4 questions, each will be having 25 marks, okay. So I hope for the first question you can get 25 marks, okay. Okay, so second questions is related with statical multipath channel, multipath model, okay. This statical multipath channel model, okay. So your second question will be based on this this one, okay. So basically you should have the idea what is autocorrelation, what is cross correlation, power spectral density, okay. So these things you need to know, the coherence bandwidth, this one, okay. So these things basically you need to know, okay. And okay, so these things you should know. And also uh, so you will be having narrow band fade in models and wide band fade in models, okay. So both will be having, okay. Under narrow band, what is that? 58, no? So this is a statical multipath channel, okay. So just see these things, okay. And I think you will be having one question related with this one, okay. I think we have done this now, this kind of question, okay. So you will ask to find, so wideband channel fading, you will be have the same question like this, okay? So you will be given autocorrelation function, okay? And you are asking to find average delay spread and RMS delay spread, okay? So average delay spread, you can find using this one, okay? So the okay. Uh, okay. So this is the power delay profile, okay? This is the power delay profile, okay? So so this integration, using this integration, so you will be given the power delay profile, is specific power delay profile like this, okay, like this, and you will be asked to average delay and RMS delay, okay? So you can use these two equations. So you need to do the integration, okay? So this integration divided by this integration, and you need to have this integration, and you need to have the square root, okay? And one questions you will get using this, you will get around maybe 12 marks for this one. I think you can easily get that one, okay? Because we have done one questions, okay? And uh, there are some parts. Where is that Rayleigh model, Nakagami model? Where are those? It should be under the multi-part pairing module, no? Okay. So this Rayleigh distribution related questions also you will be having, okay? And maybe you can try to derive this one, okay? For example, if this X and Y are Gaussian variable, if this X is a Gaussian variable, normal variable with some mean, with a mean and one variance, okay? And Y is also another normal distribution, Gaussian distribution with another mu and another variance. Okay. Okay. And if you get the square, and if you get the square root, okay. So this, and if you get square, x square divided plus x square plus y square, okay. And this will be a Rayleigh distributed variable, okay. X square plus y square. Let's say that it is z square. So this z square will be a Rayleigh. variable, okay, Rayleigh distributed variable. Maybe you can see it in MATLAB, okay. So you can generate a normal distribution and you can generate another normal distribution, then you can get the scan. If you find this, if you plot this Z, you will be having a Rayleigh distribution like this, okay. This is the Z, okay, Z square actually in this case, and this is the probability, okay. This is the probability of Z square, okay. So you will be having this kind of graph, okay. So this is the Rayleigh distributed graph, okay. And if you get the square root of this, okay, Z square root, Z square root, that is the Z, okay. That means square root of this x square plus y square, okay. So it will be a exponential distributed signal, okay, exponential distributed signal, okay. So just see them, okay. And this is the PDF probability for exponential signal, okay, exponential signal, this one or this one, okay. So you can see that these are yeah, the Z part is there, no? Maybe, okay. So if the Z is also there, maybe it will be a no, this is a Rayleigh distribution, okay. This is a Rayleigh distribution. Yeah, this is the Rayleigh distribution, okay. This is a Rayleigh distribution equation, okay. This is the probability density function of Rayleigh distribution, okay. Rayleigh distribution. This should be a Rayleigh distribution equation, okay. And actually this will be the exponential, okay, because you can see that this is exponentially, the x is the variable and these are constant, okay. So it is e to the power minus x. So this one will be a exponentially distributed signal. This will be the exponential distributed signal. No, I think I got, I mistake, okay. Actually, if you get, if you have two random variable x and y, okay, I'm sorry, I have done a mistake, okay. X and y normal distributions variable, Gaussian distribution variable, and if you get, if you square those two, and if you get the square root, okay, so this will be a Rayleigh distribution, okay. So this is the Rayleigh distribution actually. I just interchange, okay. This is the Rayleigh distribution, okay. And you need to get the square root, okay. So this is the Rayleigh distribution, okay. And you can see this in MATLAB actually, okay. So this is the Rayleigh distribution. And if you square this, so Z square, that is S square plus Y square. So this will be a exponential distribution, okay. So if you get the square root, you will having this kind of PDF, okay. This is the PDF function, okay. And this is not exponential, okay, because Z is here. This Z is the variable. So Z is here. So this is not exponentially vary, exponentially changing, okay. But if you consider this one, if you get the square, Z square, then this will be a exponentially distributed signal, okay. Okay, so maybe this kind of this, do this example, this one also, okay. So actually this is not much difficult, okay? So you can see that here you are asking to find the under relay fade in, okay? Under relay fade in, average received power. Okay. So I think this is not much difficult, okay? Okay. So so you are asked to find you are asked to consider a relay fading channel, okay? And it is said that average received power will be 20 dB, okay? And maybe I told you that, okay, if you consider a Gaussian variable like this this variance sigma square will be the power, average power of the signal, okay? If this is a random signal X, okay, and the variance, this is related with the power. This sigma square is related with the power, okay? So here also same as if you consider this, this is exponential distribution, okay? Okay. Uh, okay. This is the power distribution, no? Yeah, this is the power distribution. This is the power distribution. Okay. This one is the power distribution and it is exponential, exponentially varying PDF. It is just like this. Okay. It is exponentially varying. Most probably this is minus, no? So it is like this. Okay. So this kind of variation here. Okay. And you can see that. Uh, so uh, this PR, that is the received power, okay? So that is the average received power is 20 dB, okay? And this PR is in watt, okay? So you can convert this 20 dB into watt, milliwatt, okay? So 20 dB milliwatt, it will be 100 milliwatt, okay? And, okay, 100, okay? So, so you are asking to find the probability that received power is below 10 dB, okay? So let's say that here this point is 10 dB. Now you are asking to find the probability that below the 10 dB may be here, this probability. So how we get it? You need to integrate this, no? From here to here, you need to integrate this. From 0 to 10 dB, you need to integrate, okay? Then you can find the total probability because you need to add all these probability. You need to add all these probability. To add all these probability, you need to integrate this from here to here. Okay. So this is the distribution. So you need to basically integrate this 0 to 10 dB. Okay. So the PR will be 100 milliwatt and this also will be 100 milliwatt. Okay. So very easily you can find the probability, the power below 10 dB. Okay. So this is very easy. Okay. So just try this one, okay? Uh, okay. So as I can remember, this kind of question also you will be having, okay? So you can easily find that one also, okay? Okay. And this is the power distribution of the Nakagami channel, okay? Nakagami channel. Just see this one also, okay? See this one also. Okay. So I think that is that. Okay. So that is related with questions too. Okay. So just try these things. Okay. Do this example and that I showed example for question 2. Okay. And question 3 is related with diversity. Okay. Diversity combining technique actually. Okay. Though, so the question 3 will be related with diversity, actually diversity combining technique. This one. Okay. Uh, Most probably selection combining, maximum ratio and equal gain combined. Okay. So maybe I think we have done this question also. Okay. So I ask you to do this one. Okay. So the outage probability, so this is related with BPSK. Okay. So outage probability, so for BPSK is given here. Okay. So so you can try to find this one. Okay. For the BPSK modulation. So you are given the equation. Okay. So what you need to do is you need to just substitute the value. Okay. And also I ask you to find um, this kind of one. Okay. So that is also for the BPSK because only BPSK uh, the error probability is given. Okay. So this is the average error probability. Okay. So so under BPSK is given in SC and MRC, for example. Maybe you can remember. Okay, so you can see that these are the outages for the selection, for example, in under selection combining. Okay, so the outage probability is this one. Okay, outage probability is this one. So this will be the average SNR and this will be the instantaneous SNR. Okay, so this is the average outage probability and the selection combining under. So maybe you can do this kind of one, this kind of questions for the BPSK. The equations are given. Okay. Mm, Threshold combining, I think no need. Okay. Okay. And also selection combining also maybe this is threshold combining. No? Okay. So under MRC, you can see that maybe this is the equation for the outage probability. Okay. And this is the equation for the probability of error for the BPSK modulated signal under relay fading channel. Okay. So if it is a BPSK, if it is a DPSK or something, this equation will be given to you. Okay. Okay. So if it is BPSK, not given because BPSK equations are here. Okay. So you need to substitute some value here. Okay. So maybe we have done this one. No, we have done this one. Okay. So this is uh, MRC and ECG comparison. Okay, so this kind of questions you should be able to do. Okay, so these are very easy. What you need to do is just substitute the value here. Okay, මේක එහෙම ගොඩක් හිතලා කරන්න නෑ. කෙලින්ම අර equation ටික හොයාගෙන ඒකට value ආදේශ කරන්න තියෙනවා. ඔය ගණන් දෙක තුන හැදුවා නම් ඇති. Okay, so if you done these 3 or 4 questions, okay, before the exam, so that will be enough. Okay, so these are solved examples. Okay, and others are same. Okay, just you need to substitute the value to equation. Okay, so I'm not going to do them. Okay, so that is related with question 4. I hope you can get 25 marks for the question 4 also. Okay, so actually question 1, I hope you can get 25 marks, and question 4 also, I hope you can get 25 marks. Okay, sorry, question 3 also you can get 25 marks. Okay, and question 4 is related with MIMO channel. Okay, just see the MIMO. Okay, and uh, so the MIMO, this one. Okay, 299. Okay, these are the MIMO channel. Okay. Uh, and these are related with the information theory. Maybe you have learned these things. Okay. So communication theory and information theory, these are calculating entropy or those things. So here you no need to do. Okay. Okay. So actually this one you need to see. Okay, MIMO diversity. Okay. This is the MIMO model. Okay. There will be several transmit antenna and several receive antenna. Okay. Uh, and these channel uh, gains can be represented using matrix. Okay, so there should be 3 transmit antenna and 3 receive antenna. Okay, so just see it. Okay, so this is the MIMO channel matrix. Okay, so you should be able to get the channel matrix. Okay. And, so you are asking to find the MIMO gain. Maybe you can remember that where is that? If you want to find the MIMO gain, you need to find the SVD, no? Okay, single value decomposition. Where is that? Single value decomposition. Second, we have done, okay, single value decomposition. So just try to It is some parallel decomposition of the minus channel 3. um, Yeah, this one, okay. So this is the singular value decomposition, SVD, okay. Um, so if you are given a matrix, you should be able to find this singular value decomposition of this matrix, okay. So that means you can uh, represent this matrix by another three matrix actually, okay. So we have discussed these things, okay. So actually, um, if you type this in ChatGPT, you can get to solve problem, okay. So just do that one, okay, because if we are going to do this, it will take much time, okay. So I'm not going to do this, okay. So this kind of questions maybe you should be able to do, okay. Okay. uh, so that's all, okay. So for the questions 4, I think you will be having this one, okay. And also maybe you can see uh, the gain, okay. um, Example. So maybe matrix related things, maybe you need to find the rank of the matrix. Just see that one also, okay. So just memorize how to find the rank of a matrix, okay. Rank of a matrix, okay. So the rank of the matrix, uh, just see this one also, okay. So maybe you can use ChatGPT for this one also. How to find the rank of the matrix, just see this one and also this one, okay. So I hope that will be enough, okay. So again, I will tell you there are 4 questions. The first one with the channel fading. So just do the highlighted examples and multi-part channel statical multi-part channel model. The second question. The third question will be in diversity, combining technique. Fourth question will be in mind. Okay. So I hope you can do this without a problem. You can get good marks for the paper. Paper will not be much hard. Okay. So all the things we have done. Okay. And all the things there. So you need to uh, you need to no need to have any IQ actually. Just to follow the procedures, okay? You have to follow the procedures. That's one, okay? So the equations are there. You have to substitute the value to the equation, and also this singular value decomposition also there is a procedure, so you can follow up the procedure, okay? Okay, so shall we wind up? If you have any problem, you can ask, okay? So otherwise, we can wind up the session.